These next couple slides aren't a real big issue with us because we already know about moments about a point, but what we're trying to get at over these next few slides is just, how we can look at a concept of a moment about an axis now. We already know when we take a moment about point O that it is the cross product or the vector product between a vector R and a vector F. So R could be a position vector and F could be a force vector. When I look at the scalar moment about an axis, and let's say this would be the axis OL, we get into what are referred to as triple vector products, which is the dot product between one vector and the combination of a cross product of two vectors. So the way that we'll express that is by a unit vector lambda. We've seen this unit vector used before, multiplied by the dot product of the moment vector about point O. So in this case, I'm taking vector R cross product with vector F, and I'm using that as a quantity, as a vector actually, and I'm using the dot product between that and a unit vector, which I'm calling lambda. Again, we can express this in a different way. If I look at this axis BL, okay, I've got a unit vector which is acting along that axis, and I'm going to do a dot product with the moment vector MB, which is again the cross product of a position vector R, again R A relative to B. B is the point that you're sort of coming from, okay, multiplied by the vector F. What you should realize is I could slide, this anywhere. I mean, I don't have to be at point B. I can be anywhere along this axis, and it's really independent of point B. I will, as long as, again, that position vector R, RAB or RA minus RB is the same, you're going to end up with the same answer. They showed a sample problem 3.5. There's a few problems with this. I'd probably refer back to the book, but we'll do the best we can in here. It says, I've got this force down there on F, and what I'd like to do is calculate the moment of that vector P about point A, and then about edge AB, and then diagonal AG. So anyway, on this, there's a couple problems with these slides, but we'll let it, try to point those out. You can refer back to the book. I think the book's pretty solid in this regard. The first thing on here is, and we've done this now several times, what's the cross product of the position vector of the force P about A? Now P is down there at F. I'm summing moments, or I'm calculating a moment about point A. So again, I look at the position vector of F relative to A, or basically you can think, hey, I'm at A and I'm walking towards F. How do I get there? In this position vector is A, since I'm moving A in the x direction I, minus AJ, because again in the y directions, when I'm coming from point A down to point F, I'm dropping the side of the cube, okay? The vector P, here's where there's a problem, one problem in this set of slides. They say P times the quantity of 2I plus 2J. That's wrong. That should say P is equal to p divided by square root of 2j minus p divided by square root of 2k. So again, that p vector that they're showing there is wrong, okay? When they actually calculate the moment at A, they come up with the correct moment. That moment at A is what AP it should be AP divided by square root of 2 times I plus j plus k. So a couple problems with that. And again, what I would do is go back and sort of take a look at the textbook. I think it's like page 90 or something like that. So anyway, that's what the moment is. Again, that should say AP divided by square root of 2 I plus j plus k. All right. Then when we try to take this relative to an axis, the first thing that they do is say, hey, let's go about an axis AB. All right. So from what we just talked about, what we do is take the vector, the unit vector that axis lies in or acts in. In this case, AB is exactly 1 unit in the I direction. Okay, so AB, that axis, is exactly 1 unit of I, all right, or 1 unit A in the I direction. So we're going to dot product that with the moment. Again, the moment at A should be AP divided by the square root of 2 I plus j plus k. So in this case, the dot product of I times I is 1. The dot product of I times j is 0. The dot product of I times k is 0. So the moment about line or axis AB is should say AP divided by square root of 2. Okay, and again, the triple product between a cross product and then a dot product is going to be a scalar quantity, but that actually should say moment AB about AB is AP divided by square root of 2. The next one up here says, hey, let's do this again, this triple product about a new axis, AG. Only thing I can say with this, again, the moment down there at AG that they calculate up now is correct. Okay, it should say negative A times B divided by the square root of 6. So that's all right. The unit vector, the blue line, again, we do that by position vectors, and I think they got this position vector backwards. It probably should say, well, probably should say G relative to A, because your unit vector's up there at A, so you're coming from A. All right. If you look at that, it is a positive A in the I direction. It is a negative J, negative A in the J direction. It is a negative A in the K direction. So the little lambda unit vector is correct there. That all looks pretty good. It should say 1 divided by square root of 3 I minus J minus K. So what we're going to do is take that unit lambda vector and dot product it with the moment at A. Now here, the moment at A, you can see that they've actually divided by square root of 2, so that's correct now. So we'll dot product that with between the lambda and MA to get MAG. Now again, I times I equals 1, I times J, I times K is 0, J times J is equal to 1, negative J times positive J is negative 1, and so on. So anyway, the answer down there where you see AP divided by square root of 6 times the quantity of 1 minus 1 minus 1, the reason you have that is I times I is 1, negative J times positive J is negative 1, negative K times positive K is negative 1, so you end up with a negative 1 down there. Okay?